Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be talking about the problems in rigid body dynamics part 2. We will be starting our discussion with a new rigid body, the so-called gyroscope. The gyroscope is a special case of the spinning top where its angle that it makes with the fixed axis is 90 degrees. So the gyroscope is a horizontal version of the spinning top. So without waiting, let us continue. So problems in rigid body dynamics. Problems in rigid body dynamics part 2. Okay, so then we are talking about gyro compass. We are talking about gyro compass. So this is the smoothly pivoted to so that the center of mass is fixed. So the CM is fixed, right? And the axis of symmetry remains horizontal, and the axis of symmetry GX1 remains horizontal. So what we have is that here is the axis of symmetry, so GX1, and we have that this is the case where the gyroscope has this vertical axis. The gyroscope's spinning axis is always horizontal, and it is spinning about the horizontal plane. So this is my x1 prime, and this is the angle that it spins around in the plane. And we always know that theta is always 90 degrees, so that is fixed. And then of course my x3 will never change, so x3 is always fixed. So we have that my x2 is going to change as well with x1, right? So these are the different axes that is happening. Okay, so then what we have is that gx1, so as I just said, gx1 prime is horizontal, so this remains horizontal, and the gyroscope is free to rotate about gx1, so it can, so depending on the conditions, it is going to rotate about the horizontal. So free to rotate about gx1, prime, and this is useful in navigation. So this is typically a navigation device, useful in navigation. Okay. So now let us, it turns out that the rotation of the gyroscope is also very much impacted by the rotation of the earth. So let us look at a simpler case where we first neglect the rotation of earth. So let us look at the case where we have non-rotating earth. So earth's rotation is neglected. Okay, so let G, x1, x2, x3 frame is fixed to earth. Right, with gx3 pointing vertically upward, vertically up. So it turns out that the axis of the gyro is moving in the x1, x2 plane, right? And we have that gx1, x2, x3 prime. Well, x3 is the same as x3 prime. So gx1 prime, x2 prime, x3 is now rotating, is the rotating frame, and along the axis of symmetry of the gyro, right? So then we also have that the Euler angle theta is pi by 2. This is fixed. So this is the special case of a spinning top. And then The only coordinates that we have to worry about is phi and psi. So the gyroscope is also, there is also a nutation of the gyroscope. Well, not nutation, but the other two Euler angles are the generalized coordinates. So then, if we were to write the angular velocity of this gyroscope, the angular velocity will be psi dot E1 prime plus a phi dot E3, right? The only two angles of rotation. So now what we have is that CAA, these are my principal moments of inertia. So the principal moment. So essentially C is my gx1, the moment of inertia about the axis gx1. Okay, so then the gyro is now free to rotate. So what have we got? So it turns out that there exists a moment. There is a moment about the second axis, the gx2 axis. So about the gx2 axis. So gx2 plane. So there is a moment about the gx2 plane, that is d dt of Lg is d dt of C psi dot E1 prime plus a phi dot E3 prime, E3, and this is equal to K E2 prime. So it turns out that there is a moment about about the second axis, about this axis, which allows the gyroscope to have this angle theta equal to 90 degrees, or it allows the gyroscope to rotate along the horizontal plane. There must be a moment, right? So that is what we have written, the moment equation. So let me call this equation 1, and then so then if we expand this this equation on the left hand side, we see that we get, so from 1 we identically get that this is C psi double dot E1 prime plus C psi dot DE1 prime dt plus a phi double dot E3 is equal to K E2 prime. So then what we have is that DE1 prime dt is DE1. Well, we are using some chain rule so that we can now use some results. So notice that our E1 prime, that is the moving axis E1 prime and E2 prime, they are quite analogous to r hat and theta hat in polar axis, right? So which means that the following results hold for the derivative. So dE d phi is equal to E2 prime, and dE prime d phi. So this is dE1, this is dE2, this is E1 prime with a minus sign. Okay, so if we use all this information in this equation 1, we are going to get that, well, and we equate component wise. We equate the E1 component with E1, which is 0, E2 component with E2, which is K, and E3 component with E3, which is 0. So from here we get three relations, that psi double dot is 0, the E1 prime component will not be matched, and then will be matched to 0. Similarly, phi double dot is 0, and the third result is that is C times psi dot phi dot is the moment K. Now from here, the first equation we can integrate, psi dot is n, and the second equation we can integrate, phi dot is omega, and then we can integrate this out. We can integrate, well, so psi dot is n, this is a constant, and phi dot is omega. We can plug all this information in the third relation. We get that C n capital omega is K. So this is our gyroscope equation. for which there is a moment about the E2 axis. So the gyroscope has a constant spin, so n is the spin, and it rotates about the E3 axis with constant angular velocity omega, right? So then let us now look at the case with the Earth's rotation taken into account. So this is the case when we have the rotating Earth. Okay. So this is the case when, so let G, x1, x2, x3 are the axes fixed at some location. This is the axis which is fixed at some location on Earth with Gx3 in the local direction, the local vertical direction, and Gx1 points north and Gx2 will point west, right? So Gx1 north and west means that we have x1 along this direction and x2 along this direction, and so on. So Gx3 is the top vertical. Okay, so same idea. And now then, so we suppose that this is my non-inertial frame or the fixed frame, the non-inertial frame which is rotating with the Earth's angular velocity, omega. Okay. So then what we can do is that we can write down this. So we will try. So this is my fixed. This is the rotation of the Earth, omega e. Now, if we were to write this angular velocity of the Earth in the moving frame, that is in the gyro frame, then my omega e. Now this is with a bar. So this is the moving frame quantity. So omega bar is omega e sine alpha cos phi E1 prime minus sine phi E2 prime plus omega e cos alpha E3 bar. Okay, so E3 bar is the same as E3 bar prime because this is the same vertical in both the axes. So here we are, we have found the impact of the Earth's rotation on the moving frame. So now if we were to write the angular velocity of the gyroscope. So what is the angular velocity? The angular velocity of the gyro, we see that omega this time is going to be psi dot E1 prime plus phi dot E3. These are my two components plus omega e and my LG is the angular momentum is Ig, the moment of inertia about the center of mass times omega, and we can start to use this information. So this is C times psi dot. So psi omega bar is the moving frame, so we have to look at each component. So this itself is a vector here. So now the E1 prime component will be psi dot plus omega e sine alpha cos phi E1 prime minus omega e sine alpha sine phi E2 prime and plus a of phi dot plus omega e cos alpha E3, right? So these are my three details and three components, and then we know that the rate of change of angular momentum dlg dt is k times E2 prime. Okay, So then we can start to substitute these the angular momentum in this torque equation and see what happens. So if we do that, so let us call this as our expression A and our expression B. So from expression A and B, we find that we are now substituting everything. So it's going to be a giant equation. So C times d dt. Well, I'm not going to write all the terms. It's a giant equation, but the issue is we plug in this angular momentum into the torque equation and take into account the fact that we will use substituting A into B and using the fact that dEj prime dt is equal to omega star cross Ej prime. And then where my omega star is the angular velocity of the frame gx1 prime, x2 prime, x3, right? And then we will be using this result in the expansion. Okay, so then my omega star comes out to be phi dot E3 plus omega E, right? So what we get is we can expand this omega E into the moving frame and we are going to get the results that this is this entire expression is omega E sine alpha cos phi E1 prime minus omega E sine alpha sine phi E2 prime plus phi dot plus omega E cos alpha, and this is my E3 vector, and this is set equal to 0. And now we will have three sets of equations. The first equation, what have we got? We have one equation which should be non-zero. So this is the one. So what have we got here? So so one psi E, this E1, and then E2 and then E3. So now if we equating E1, E2 and E3 components, we get that we will get set of three equations for each components here, 1, 2 and 3, and we are going to get that so omega star is psi dot plus this quantity, right? So we get first equation is psi dot plus omega E sine alpha cos phi. So this is this quantity here, and similarly the second, this is set equal to 0. So this is my E1 prime component, and then similarly I can find out what is E3 component. So E3 is omega, A phi double dot plus omega E sine alpha times C times psi dot plus omega E sine alpha cos phi minus A omega E sine alpha cos alpha sine phi. So this is equal to 0. So this is my E3 component, and finally my third equation is the spin equation. So omega dot E1 prime is a constant which is given by n. So then these are my equations, and so from this equation number 2 and 3, what we find is we can find we can eliminate psi dot and we can find an equation for phi. Equation for phi. So what is the equation for phi? We see that this is a phi double dot plus omega e sine alpha times Cn minus a omega e sine alpha cos alpha sine phi. This is set equal to 0 and this is my equation number 4. Right? So typically we expect that this ratio, so generally the ratio a omega e by Cn, this is much less than 1, and so which means that this quantity in the bracket is roughly equal to Cn. Why? Because AE is a very small quantity compared to Cn, and then we can now conclude that this equation number 4 is the equation for large oscillation about phi equal to 0. So so this is the case of large oscillation about phi equal to 0 or about the gx1 axis, about the gx1 axis. Okay. So now if x1 points north, then the gyro becomes periodic oscillations about the northerly direction. So that is the conclusion of this statement. Okay, so we can quickly get some problems done. So here is one quick example. It says estimate period of small oscillations of the gyro. Okay, so typically we have again, so the equation for phi comes out to be a phi double dot plus Cn omega e sine alpha times phi, which is 0, and this is the equation for large oscillation where we have used the approximation, right? And so from here, if we integrate this equation for phi, we get the period of oscillation for phi, the tau, to be 2 pi divided by square root a divided by Cn omega e sine alpha, right? And then what we have is that omega e comes out to be 7.3. Well, this is the period of the Earth's rotation. This is the angular frequency of the Earth's rotation, 10 to the power minus 5 radians per second, and c is equal to 2a, and alpha, if suppose alpha is 45 degrees, and further if we take the value of n, the spin, to be 50 per second or 50 hertz, then we see that the period of small oscillations of the gyro comes out to be roughly 35 seconds. Okay, so this is typically of the order of oscillations of the gyro is typically in the order of seconds. Okay, so then we can now talk about the Euler angles again. We are coming back to our description of Euler angles. So let us say we look at an axis which is embedded in the body of the embedded in the rigid body itself, right? So suppose we look at an axis x1 which is embedded along the rigid body itself. So this is omega, and this is the body fitted frame now. So what I am saying is, so we are looking at the Euler equations of motion. The Euler equations are the equations of motion in the rotating frame. So suppose the principal axis is rigidly fixed or embedded within the body, right? Within the body. Right? So what we see is that the angular velocity the angular velocity of the frame is the same as the angular velocity of the body, right, in which it is embedded. And now what we get is that E1, E2, E3, these are my unit vectors in the body fitted frame. So these are the unit vectors in G, X1, X2, X3 frame. And what we see is that for this, the angular velocity omega can be written as omega 1 E1 plus omega 2 E2 plus omega 3 E3. And then we have the angular momentum Lg. This is A omega 1 E1 plus B omega 2 E2 plus C omega 3 E3. And similarly, we can find the torque equation dLg dt is kg. So that's the torque equation. This is where kg is my external moment, right? And then we can start to plug in all these values to see what happens. So if we were to start plugging in the values of the angular velocity in the torque equation, we see this is what happens. So we get this long equation A omega dot 1 E1 plus B omega 2 dot E2 plus C omega 3 dot E3 plus A omega 1 dE1 dt plus B omega 2 dE2 dt plus C omega 3 dE3 dt. And then this is going to be KE1 plus, K1 E1 plus, we are looking at the general torque here, K1, K2, K3 are its components. And then if we were to, look at each component of this giant equation, we are going to see that this is A omega 1 dot minus B minus C, omega 2, omega 3, this is K1. And then similarly, we will have a set of two more symmetric equations, B omega 2 dot minus C minus A, omega 1, omega 3 is K2, and C omega 3 dot minus A minus B, omega 1, omega 2 is K3. So these are my so-called my Euler's equations. So this is the equation of motion in the moving frame, the Euler's equations, right? So let us look at an example. So the problem says, I think I am getting all out of time here, and in the next module we will talk about some examples involving Euler's equation, and eventually we will look at the so-called the T ellipsoid and the L circle. Okay, so thank you so far for listening.